In this problem, we're presented with the addition of two strong acids to one another. So these acids aren't going to react with one another. Rather, what they're going to do is they're going to compound the number of moles, and we're going to see what effect that has on the total concentration. So anytime you add together two acids, you want to find the total number of moles of H+. And from there, we'll be able to figure out more about the pH, or in this case, pOH. So first, let's figure out the number of moles provided from each acid. Remember, strong acids dissociate completely, and we can use the relationship that moles are equal to molarity times liters. So I'm just going to take for this first one, for the HCl, it's 0.34 molar HCl, which just basically means H+, times 0.3 liters, 300 milliliters, to get 0.102 moles of H+. Okay, part 1, done. Now let's figure out how many moles we're getting from the perchloric acid, the HClO4. So that's 0.10 molar of perchloric acid, which is just a source of H+, times 0.5 liters, the 500 milliliters, which is going to end up equaling 0.05 moles of H+. Now, we want to know the total moles. So all we have to do is add these two values together, and we'll end up getting that there are 0.152 mole of H+ total. It's a funky looking H. Since the question is asking for the pOH, that means we're going to need to turn this into concentration so that we can get the pH, and then we can easily find the pOH. So the H+ concentration is going to be equal to the moles divided by the total volume. The total volume is going to be the 300 milliliters plus the 500 milliliters, which means a total of 0.80 liters. So our H+ concentration ends up being 0.19 molar. Taking the negative log of that will give us the pH. The pH here happens to be a cool 0.72. Pretty acidic solution we got going on here. So then to get the pOH, we need to do 14 minus that value. So 14 minus 0.72, which will end up equaling 13.28. Choice A. In this problem, we're asked to find the strongest acid, and we're given a bunch of constants here that we can use to help us in our quest to do so. So first, I'm going to eliminate a few answers here. So we want to know the strongest acid. Well, looking at these Ka values, we can see that some of them are stronger than others. So out of these three, the phenol is the weakest, then the hydrogen cyanide, and then the acetic acid is the strongest of these three. So right off the bat, using just the Ka values, we can eliminate a few of these answer choices. Let's do just that. So then we're down to 3 left. Well, I'm going to go ahead and eliminate C6H5O-, because that's just the conjugate base of phenol. If acetic acid is a stronger acid than phenol, that means it must be a stronger acid than phenol's conjugate base, right? That would just be wacky. So, we're down to 2. Now wait a minute. C5H5NH+. We don't have a Ka value for that. But can we find one using information that we're given? I would argue yes. So this is protonated pyridine. which is just the conjugate acid of pyridine, which we are given above. So I'm going to use the relationship that Ka times Kb equals Kw to find the strength. And then we will know once for all which is the strongest of these acids. So, plugging in values, we get Ka of the protonated pyridine times the Kb, which is equal to 1.7 times 10 to the negative 9th is equal to Kw, which is 1 times 10 to the negative 14th. Great! Now let's solve and find out what the Ka is. Turns out that the Ka of protonated pyridine, C5H5NH+, is equal to 5.9 times 10 to the negative 6th. Well, if we compare all of them, that's still actually less than acetic acid. So acetic acid is going to be our strongest acid of the three. Ascorbic acid, aka vitamin C, is, well, appropriately enough, an acid that we can find in many citrus fruits. And we want to know the concentration, or we want to know rather the pH of a solution of ascorbic acid, given the molarity. A weak acid? Trying to find the pH. When in doubt, I sit down. So, remember, all weak acids are going to use a Ka dissociation, where they're going to simply take a proton and drop it as if it's hot, leaving behind the H plus and a conjugate base. So we're going to set up our ICE table here. 0.0023. Unless told otherwise, we're starting with 0 of this and 0 of that. This will be minus x plus x and plus x to get 0.0023 minus x. 0 plus x is x, and 0 plus x is x. Okay, now we need to write out our equilibrium expression. So our equilibrium expression for this is going to be Ka1, since this is the first dissociation, is equal to the concentration of H plus times, we're just abbreviating the ascorbate as HASC rather than writing out the entire thing, all divided by the initial concentration of ascorbic acid. It's important to point out here that for a polyprotic weak acid, if you're trying to find the pH of a solution where you're just dissociating the fully protonated acid, a vast majority of the protons are coming from Ka1. Look at how many times bigger Ka1 is than Ka2. This is on order of magnitude of, yikes, like 10 million times greater. That means that whatever protons are coming from this dissociation are going to be insignificant in comparison. Now we're going to plug our values into our equilibrium expression. So 8.0 times 10 to the negative 5th is equal to x times x squared over, and remember there's a nifty little shortcut we can use in this class. Since our k is on order of 10 to the negative 5th or less, we can just take this x and drop it as if it's hot, because it's going to be insignificant compared to this 0.0023 that was initially in there. So I'm just going to plug in the 0.0023 into this equation. We'll multiply the 0.0023 through and take the square root. And once we do that, we will end up getting that x is equal to 4.29 times 10 to the negative fourth. And remember, that is also our H plus concentration. So what we're going to do now is to get the pH, we'll take the negative log base 10 of that value that we got. And we'll end up getting that the pH of the solution is 3.37. Most of the time when we do acid-base problems, we're at a nice, cool temperature of 25 degrees Celsius, standard temperature, where Kw equals 1 times 10 to the negative 14th. But every so often you might come across a problem where our Kw is something different. Now, because the Kw is not 1 times 10 to the negative 14th at this temperature, this changes the way that we have to approach this problem. Sort of. It just means that we can't use our old constant where pH plus pOH equals 14. But we can still use the fact that pH plus pOH equals pKw. That's universally true. So really the only thing that makes this problem different from a 25 degrees Celsius problem is that we need to figure out what pKw is in order to solve this problem. Remember that P means the negative log of something. So pKw at this temperature means the negative log base 10 of 2.51 times 10 to the negative 14th, which will end up equaling 13.6. Okay, now we can go about trying to find the pOH of the solution. Since the pH here is equal to 7.4, we'll plug that in, plus the pOH that we're solving for is equal to the pKw, which is 13.6. So we'll subtract the 7.4 from both sides, and we'll end up getting that the pOH at this temperature ends up being 6.2. Okay? In this problem, our goal is to figure out which of these sparingly soluble salts will precipitate out first. So in order to do that, we need to find the tipping point. The tipping point is where your solution is saturated. That is, the concentration of ions you have is equal to your KSP. So all I'm going to do here is find out how much bromide would be necessary to reach saturation. So to do that, I'm going to write out an equilibrium expression for both of these. So let's just write out the reaction, because it's always good to start with a reaction. For silver bromide, our reaction is AgBr, solid, dissociates into Ag plus, aqueous, and Br minus, aqueous. So KSP of this reaction is just equal to the concentration of silver plus ion times the bromide ion. Now, we're going to figure out what concentration of bromide ions is necessary to get this salt to come out of the solution. So, taking our KSP, which is given to us, it's 7.7 times 10 to the negative 13th. That's going to be equal to the concentration of silver, which was also given to us up here. So 2.0 times 10 to the negative 4th times the bromide ion concentration needed to reach saturation. We'll divide both sides by the 2 times 10 to the negative 4th, and we'll end up getting that the bromide ion concentration necessary to get this to precipitate out is going to be 3.9 times 10 to the negative 9th. So what that means is, once we add in this concentration of bromide, the solution will be at equilibrium. It'll be at saturation, and any more will cause the silver bromide to crash out of the solution. Now let's figure out how much bromide it would take for the lead bromide to precipitate out. So the math's going to be slightly different here, because lead bromide breaks apart into 3 ions. So it would turn into lead 2 plus, aqueous, and 2 bromides, Br minus, also aqueous. So that means that KSP is equal to the lead 2 plus times Br minus squared. All right, let's plug in our values and find out how much bromide it would take to make a precipitate. So 6.6 times 10 to the negative 6 is our KSP value for lead bromide. We're given our lead concentration above, so that's going to be 1.5 times 10 to the negative 3rd. And then that's going to be times the bromide ion concentration squared. So I'm going to divide both sides by the 1.5 times 10 to the negative 3rd. When we do that, we'll end up getting 4.4 times 10 to the negative 3rd is equal to the bromide ion concentration squared. And then we'll take the square root of both sides. And for this one, it turns out it's going to take substantially more bromide to get this to precipitate, to the tune of 6.6 times 10 to negative 2 molar. So if we compare the two, we can see it takes a whole lot less bromide to make a precipitate of silver bromide. So in terms of what will precipitate first, it's going to be the silver bromide. Okay? Remember, just quickly to emphasize this point, any group 1 metal salt is going to be completely soluble in an aqueous solution. The only reason why that Na is there, as we're adding in the salt, is because you can't just add in bromide, Br minus, into a solution, because that would be negative charge and that'd be super unstable. So this is just coming along for the ride to help the bromide. Okay? Great. Oh no! There's been a catastrophe in the lab of Rick T. Cat. 3 acids were mixed up, and we need to figure out which acid is which. Well, let's look at what acids we have. We have acetic acid, we have hypochlorous acid, and we have nitric acid. So first things first, nitric acid. What do we know about that? It is a strong acid. So looking at these titration curves, which one of them, is it acid 1, acid 2, or acid 3, corresponds to the titration of a strong acid with a strong base? Well, it's going to be acid 3, right? Because look, it's super acidic, and then whoa, the pH spikes up. If we look for the equivalence point here, the halfway point of this jump, we'll see that it corresponds to a pH of 7, which is true for a titration of a strong acid and a strong base. So, right now off the bat, we've identified that acid 3 must be HNO3. Cool. But now we're left with two other acids that we need to identify. So remember, the weaker the acid, the greater the pH is going to be at the equivalence point. Because at the equivalence point, you're creating all conjugate base. So, by looking at this, I'm going to find the equivalence points of both of these. This is for acid 1. Then for acid 2, let's use a nice orange here. Here, the equivalence point, the spike in the pH is about here. So, okay. We can see that acid 2, the pH is more acidic at the equivalence point than it is for acid 1. Well, since the pH is lower for acid 2, that must mean that acid 2 is a stronger acid than acid 1. So, since the strength, that means the Ka of acid 2 is greater than the Ka of acid 1. So, which one is which? Well, it appears that acetic acid is the stronger of them, and then hypochlorous acid is the weakest, given these K values. So, that means that we can say, for certain, that acid 3 is HNO3, acid 2 is acetic acid, so I'm just going to write that in here, acid 2, and then this must be acid 1, the weakest of the three. So, which of these matches up with these data? It's going to end up being choice B. Okay, so in this problem, we're trying to dissolve a sparingly soluble salt by coupling the reaction with a complex ion formation. So, we have here written out our KSP reaction for zinc hydroxide. Very small KSP, doesn't want to dissolve that much. We also have here our KF for this complex ion formation. And wow, we can see that is a pretty notable K. The idea is by coupling together these two reactions, we'll be able to get a favorable reaction to dissolve the sparingly soluble salt here. So I'm going to write the overall reaction. The overall reaction, well, let's see here. The zinc ions are going to cancel out. So we're going to get zinc hydroxide solid plus, well, these two hydroxides are going to cancel out. This will become 2, so plus 2 hydroxides yields zinc hydroxide complex ion thingy, to use the technical term for it. So there's our reaction, but now we need a K value for this. So just recall, whenever you couple together a KSP reaction and a KF reaction, or really anytime you couple together any reactions, you can always come up with the overall K by multiplying together the two values. So we're going to take KSP times KF, so it's the KSP of what's being broken, times the KF of what's being formed, and that is going to give us our overall KEQ. So when we do this, we end up getting KEQ equals 138. Okay, now we have our KEQ and we have our reaction. The last thing we want to do is find out the concentration of hydroxide that we would need in order to dissolve this. Remember, for KF problems, we can use the ice table remix. And what I mean by that is we know that we want to dissolve 0.015 moles of this zinc hydroxide. Okay? Well, we can't officially have a concentration of a solid, but we know that we want to dissolve the 0.015 moles of this in 1 liter of solution. So we want to convert all of that into the zinc hydroxide complex. We want it to be all swept into that. So it's that many moles per liter. So this part is actually less complicated than it might seem. We'll write our equilibrium expression, which is for zinc hydroxide complex, divided by the hydroxide concentration squared. So actually, all we really want to know in this problem, long story long, is what amount of hydroxide is needed to coexist at equilibrium with 0.015 molar zinc hydroxide. So now we know this concentration, we know the end molarity that we want, we know our KEQ, we can solve for hydroxide. Let's do just that. 138 is going to equal 0.015 divided by the hydroxide concentration squared. So we'll multiply the hydroxide concentration squared through and get 138 times the hydroxide concentration squared is equal to 0.015. Then divide both sides by 138 and take the square root. And we will get that the hydroxide concentration is equal to 0.01, or 1 times 10 to the negative 2. In this problem, we're doing a titration of hypobromous acid, a weak acid, with sodium hydroxide, a strong base. So, this is one of our 3 types of titrations. Weak acid with a strong base. When in doubt, isf it out. Anytime you have a titration, anytime you add a strong acid or strong base to a solution, you're going to want to do an ICF table. So this is our reaction here. Remember, it doesn't matter what hydroxide, or rather what strong hydroxide we use. The Na plus is just coming along for the ride. What matters is that we have a source of OH minus here. Okay? So our reaction is going to be hydroxide plus our weak acid. And the hydroxide is going to be all like, give me all your protons. Again, it speaks kind of like Batman in the Christopher Nolan version of the movies. And that's why we're going to use a full-headed arrow here, because when these things react, when strong things react, they react all out. Okay, we'll write our ICF. And remember, the key difference with ICF tables from ICE tables is that ICF tables use moles. So first we want to find the concentration of HBRO. It's going to be 0.2 molar HBRO times 0.1 liters to give us a total of 0.02 moles of that. We'll do the same thing for the sodium hydroxide. We'll multiply the concentration by the volume. So 0.1 molar hydroxide times 0.4 liters equals 0.04 moles. Okay, now we can plug these values into our ICF table. So we plug in a number of moles. We don't have any of the BRO minus, and we don't care about the water here. It's not going to make a difference. And then we look for a limiting reagent. Now, interestingly, here the hydroxide, we actually have more of that than the HBRO. So the weak acid is actually the limiting reagent, which means we're going beyond the beyond the equivalence point. So minus 0.02, minus 0.02, and plus 0.02. So now, oh no, what do? We've gone past the equivalence point. How can we possibly find the pH of a solution like this? Well, it's actually easier than it looks. We have hydroxide, a strong base, and this hypobromite, BRO-, together in a solution. Now, compared to the hydroxide, is the BRO- really going to make a difference compared to the OH- in terms of the pH? No. No, it's not. So it turns out we can actually just ignore this. Anytime we go past the equivalence point in titration, just look for the strong base or strong acid that's left in excess. So really, actually, all we have to do here is find the concentration of hydroxide. So 0.02 moles of hydroxide divided by the total volume of the solution. So that's 0.50 liters. I got that from adding together the 100 milliliters plus the 400 milliliters. This is going to end up equaling 0.04 molar hydroxide, which means we can take the negative log of 0.04 to get our pOH. The pOH of the solution is going to equal 1.4. And then we can subtract that from 14 to get our pH, which will be 12.6. Okay. In this problem, we're given a Ka value for sorbic acid, and we're given a solution of this potassium sorbate, or as I like to call it, chikuk. So the first thing I always like to ask myself, is the thing that we have a solution of, in this case the chikuk, the same thing that we're given a Ka value for? And indeed it is not. But we'll see that there's striking similarities between the two of these things. How are they related? Well, this is a weak acid, and this is just the salt of its conjugate base. Let's clean up this canvas a little bit. We have here what this salt will do in an aqueous solution. Any salt with a group 1 metal cation will dissociate completely into its anion and its metal cation. So, it turns out that this is actually just the conjugate base in disguise! That was me trying to draw a disguise. Okay, back to the problem. So in actuality, the problem is saying that since we had 0.0428 molar of this, it's going to dissociate completely into 0.0428 molar of this weak base here. So what we have is a solution of a weak base. Do we know how to solve for the pH of a solution of a weak base? Absolutely! When in doubt, ice it out! Yeah! Whenever we have a solution of just a weak base, we always need to write its reaction with water. So C5H7COO- aqueous plus H2O. And remember, it's just going to hydrolyze this water to form the conjugate acid, C5H7COOH, and it's going to leave behind hydroxide. Okay, so remember, anytime you have a weak base solution, you always need to write the reaction with water. And in doing so, you're going to create hydroxides. Now we have everything set up perfectly for our ICE table. ICE, our initial concentration is 0.0428. We don't care, we love it. This is 0, this is 0. The change is going to be minus x. Over here it's going to be plus x and plus x. 0 plus x is x, 0 plus x is x. And this is going to be 0.0428 minus an inconsequential x. As per usual, this will end up being insignificant compared to the initial amount that we started with. At this point, I want to point out that we were given the Ka for sorbic acid. But is this a Ka reaction producing hydroxides? I should think not. This is a Kb reaction, right? This is the base hydrolysis of the conjugate base of sorbic acid, sorbate. But fear not, we can easily solve for the Kb using the relationship Ka times Kb equals Kw. So our Ka for sorbic acid is 1.7 times 10 to the negative fifth. That times Kb, what we're solving for here, will equal 1 times 10 to the negative 14th at 25 degrees Celsius. So solving for Kb, we end up getting that it's equal to it's equal to 5.88 times 10 to the negative 10th. And now we have everything we need to set up our equilibrium expression. So Kb is going to equal our concentration of products, C5H7COOH times hydroxide, OH minus, all divided by C5H7COO minus. Plugging in our values, we'll have 5.88 times 10 to the negative 10th is equal to x times x squared, divided by the 0.0428. Remember, this x is going to be insignificant compared to the initial amount of sorbate in there. And then let's solve for x and see what we get. Solving for x, we get x is equal to 5.02 times 10 to the negative sixth. Taking the negative log, remember x is the concentration of hydroxide here. So taking the negative log, we get the POH, which is equal to 5.3. And then 14 minus that will yield the pH, which happens to be 8.7.